In this application of the idea of subgame perfection, we'll analyze a game where two firms again compete based on Cournot competition, but they can choose their capacity in terms of the quantity that they're able to produce. So again, we have two firms. We'll fix the demand function at P equals 900 minus Q1 minus Q2, where Q1 and Q2 are the quantities that the firms simultaneously select. So Q1 and Q2 are the quantities that the two firms choose, and they choose them simultaneously. We'll stick with our assumption of marginal cost being 0. However, there's going to be a limit to how much a firm can produce based on the size of a plant that the firm builds. So before they engage in Cournot competition, the firms are going to select their plant size, and they're going to do this sequentially. Firm 1 chooses first, and then firm 2 chooses. Based on their plant size, they're going to have some capacity or some upper bound on how much they can produce, and always with the marginal cost 0. If a firm chooses a small plant, it can only produce up to 100 units. The cost of building this plant, or the investment needed to build this plant, is 50,000. If it builds a large plant, it has an infinite capacity, so it can produce any quantity it would like. However, the cost is much higher, it's 175,000. So the firm would have to invest 175,000 in order to build a large plant which can produce any quantity. Of course, the firm could choose not to build a plant at all. So no plant, then the capacity is 0, and the cost is also 0. It doesn't cost you anything not to build a plant. So each of these firms first picks between these three options, and then they engage in Cournot competition. Now the firm 1 is going to pick first, and then firm 2 is going to choose after firm 1 has chosen. It will observe firm 1's choice, and then make a decision as to what plant size it would like to build. Firm 1 chooses its plant size first, and then firm 2 chooses its plant size. After they've both chosen their plant sizes, they compete with one another. So the initial part of the game tree looks like this. Firm 1 moves at the initial node. It picks between no plant, a small plant, or a large plant. Following each action that firm 1 could take at the initial node, firm 2 gets to move. Firm 2 can again decide to build no plant. It could choose a small plant, or it could build a large plant. And that's the case after firm 1 builds a small plant, or if it builds a large plant. For each possible decision that firm 1 could make at the initial node, firm 2 then has an opportunity to make one of the three decisions. After firm 1 builds no plant, and firm 2 also builds no plant, neither of them is going to get any revenue, neither is going to pay any investment, so they're both going to receive a payoff of 0. So if neither firm enters, they both get a payoff of 0. If firm 1 doesn't enter the market, so firm 1 builds no plant, and firm 2 builds a small plant, then firm 2 is going to be a monopolist. And firm 2 is going to be a monopolist with the small plant. Similarly, if firm 2 builds a large plant when firm 1 has not entered, then firm 2 is going to behave as a monopolist with a large plant. What about when firm 1 picks a small plant, but firm 2 chooses not to enter? Then firm 1 is a monopolist with a small plant. If firm 1 picks a small plant, and firm 2 picks a small plant, then we have a Cournot between two small firms. If 1 picks a small and 2 picks large, then we have Cournot between a small and a large firm. Similarly, if firm 1 picks large, firm 2 picks no plant, then we have firm 1 as a monopolist. And if firm 1 picks a large plant, firm 2 picks a small plant, then we have Cournot competition between a large and a small plant. And finally, if they both pick large plants, when we have Cournot between two large plants. So in order for us to be able to analyze this game and solve for the subgame perfect equilibrium, what we need to do is to look at each of these and figure out what happens in each of these subgames. So we need to understand what a monopolist with a small plant would do. We need to understand how the Cournot competition between a large plant and a small plant would work, how it would work between two large plants, how it would work between two small plants. So we need to solve each of these subgames. And then what we can do is we can replace each of these subgames with the payoff that each of the firms would get in that subgame, and then look at this game tree again to solve for the subgame perfect equilibrium. So as we find the subgame perfect equilibria, we need to first analyze the subgames, which are the Cournot competition and monopoly situations. So let's start with the monopoly situations. So let's look at what a monopolist would do. If a monopolist were unconstrained, so if a monopolist did not have a capacity constraint, so they would solve the following problem. they would seek to choose the quantity Q that maximizes their revenue, 900 minus Q times Q. Remember, there's no marginal cost, and the only cost that they face is the fixed cost with respect to the plant size. Given that the plant size would have been sunk already in the initial part of the game, in the subgame, the plant size is not part of the decision. So that fixed cost is not going to affect the decision for the quantity that the firm is going to produce. So they're going to just maximize their revenue. The first order condition here is going to be 900 minus 2Q equals 0. So Q star, the optimal Q, is 450. The optimal revenue is 900 minus Q star times Q star. That's 450 times 450, and that's 202,500. Now, to produce this quantity, they would have to have chosen the large plant. So the cost, and that would be a fixed cost, for building a large plant is 175,000. So the profit, or the payoff, is then 27,500. So if a monopolist has a large plant, their payoff at the end is going to be 27,500. If they had a small plant, they can't reach the optimal unconstrained quantity, so they're going to have a corner solution to their optimization problem, and they're going to produce the quantity 100, because that's the most that they could produce using a small plant. And so the revenue is going to be 900 minus 100 times 100, so that's 80,000. The investment that it takes to build a small plant is 50K. So the payoff is 80 minus 50, which is 30,000 if a monopolist has a small plant. Next, we're going to look at the outcome of Cournot competition. We've seen Cournot competition a few times now, so we won't bother solving for the best response. We know that if firm I is unconstrained, then when engaged in Cournot competition, the best response of firm I to the quantity Qj chosen by firm J is 450 minus Qj over 2. So if they're both unconstrained and they both have large plants, so this is a case of large, then the quantities that they're both going to choose are such that Q1 is 450 minus Q2 over 2, and Q2 is 450 minus Q1 over 2, which means that Q1 and Q2 are both 300. In this case, the revenue for each firm would be 900 minus 300 minus 300. It's 900 minus Q1 minus Q2 times 300, which is quantity produced by either firm, which is 90,000. If one of the firms is constrained and the other is unconstrained, then the constrained firm is going to have to produce only 100, and the unconstrained firm is going to produce 450 minus 100 over 2, or 400. So if firm J is constrained, then firm I is going to produce quantity Qi such that Qi is 450 minus Qj over 2. But because firm J is constrained, it's going to produce the constrained amount, the maximum amount that it can, so Qj is going to equal 100. This means that Qi is 450 minus 100 over 2, which is 400. So the revenue for firm I, so this is the one with the large plant, is 900 minus 400 minus 100. So the total quantity produced is going to be 500, so it's 900 minus 500 times the quantity that the large firm produces, so it's 400. That's 160,000. The revenue of the firm J, which is the one with the small plant, is the same price, 900 minus the total quantity, which is 500, times 100. So that's 40,000. And finally, we need to think about the case where they're both constrained. So if they're both constrained, then they both produce a quantity of 100. So if they both have the small plants, they both produce Q1 equals Q2 equals 100. And the revenue for each of the firms is 900 minus 100 minus 100. So it's 700 times 100, which is 70,000. So let's summarize all of these in a table. We're only going to summarize here the Cournot outcomes. So if they're both engaging in Cournot competition, either firm could have large or small plant. There's 4 combinations: large, small, small, large, and small, small. If they both have large firms, then they both get a revenue of 90,000. They each have a cost, which is the investment cost of the plant, of 175,000. So their payoff in the end, their profit, is a loss of 85,000. If one firm has a large plant while the other firm has a small plant, then the firm with the large plant gets a payoff of 160,000. The investment cost for the large plant is 175,000, so their payoff is going to be minus 15,000. The firm with the small plant gets a revenue of 40,000, but the cost of the small plant is still 50,000, so the payoff is minus 10,000. The situation is reversed on the next line. And finally, if they both have small plants, they both get revenue of 70,000, they both have costs of 50,000, so they both end up with profits of 20,000. So we can take these profits in these columns, as well as the profits that we saw that the monopolists get, to fill in the payoffs from the subgames that we saw earlier. Doing that, we end up with a game tree with the following payoffs. It's now easy to solve for the subgame perfect Nash equilibrium. What we've done here is to solve each of the subgames and replace the subgame with the payoff from the Nash equilibrium of that subgame. So now we can look at this subgame and figure out what player 2 should do. Well, player 2 should pick the action that's going to give him the highest payoff. That's to choose a small plant. What about this subgame? The highest payoff again is when player 2 picks a small plant. And finally, we look at this subgame and we see that player 2's payoff is maximized when player 2 does not enter. Because when player 1 has chosen the large plant, no matter which size player 2 chooses, he gets a negative payoff, whereas not entering the market yields a payoff of 0. So player 2's best strategy here at this decision node is to choose not to enter. Now we know for player 1 what the payoff would be for each of the possible actions player 1 could take. If player 1 chooses N, player 1 is going to end up with a payoff of 0. If player 1 chooses S, player 1 is going to end up with a payoff of 20. If player 1 chooses L, player 1 is going to end up with a payoff of 27.5. So comparing 0, 20, and 27.5, we figure that player 1 is going to choose L. So we've solved for the subgame perfect Nash equilibrium. Player 1 is going to choose at their initial node, is going to choose L. Player 2, if player 1 chooses L, is going to choose N, and otherwise is going to choose S. And in the subgames, we've solved for what the equilibrium strategies are going to be. We saw that earlier from the Cournot model, and in this case from the monopoly behavior. And that's how you use this idea of subgame perfection to solve for the Nash equilibrium of this game. This game demonstrates something quite interesting. If the firm 1 had chosen a small plant, they could have both had a profit of 20. But firm 1 is able to deter firm 2 from entering the market by choosing the large plant. So what 1 does in this case, by picking the larger than optimal capacity, is to commit to being a tougher opponent to player 2 when they eventually engage in Cournot competition. And so when we're in this subgame, player 2 would not like to face player 1 in either of these cases, and therefore chooses to exit the market instead of entering. So this ability of player 1 to commit to this large plant is very helpful to player 1. So this is one of many instances where we can demonstrate the value of commitment.